Good morning. Welcome to MECH1433 Lecture 8. We're starting a new part of the course now, a new chapter in the textbook. This is in Chapter 6. And the stuff we're getting into now is going to sort of occupy most of the rest of the semester, really. So we're going to be looking at flow and piping systems. But today we're going to start off with sort of the basics about just flow and pipes and flow rates and the continuity equation and velocities, and we'll talk a little bit about commercially available pipes and tubing and types of conduits. And we'll also talk a little bit about recommended velocities for flow and pipes and tubes, which is of prime importance when we're trying to select appropriate conduits for our applications. And that's where we're going today. So when we're done today, you'll be able to explain and use calculations involving three types of flow rates, although we'll generally use just the one. We'll distinguish very carefully and very significantly between flow rate and flow velocity. They're different things, and they're closely related, and we need to get a grip on that. Mostly through something called the continuity equation. We'll find out what that is and how it works and how we can apply it and how useful it is. And we'll also use fairly extensively some data, tabulated data, for determining the parameters and areas and things that we need to know for different kinds of standard steel pipe and steel tubing. And we'll use some common recommendations for sizing pipes based on maximum flow velocity and various rules of thumbs and applications for sizing pipes. So to begin with, when we talk about flow rates, there's sort of three basic ways that we can talk about a flow rate. And each of these ways involves a quantity of fluid moving past some section of a pipe or anything else per unit time. So we can talk about the volume flow rate, and we normally do. This is the one that we mostly care about, is Q, capital Q for some reason. Same Q that we saw all through the fluid power course last semester. And it's volume flow rate, and of course, by default, in base units, it's cubic meters per second. But more fundamentally, we can talk about a mass flow rate and talk about a kilogram of fluid per second flowing past a pipe. And this is not used that often, but it's kind of more basic. And we'll see when we start off with this concept where it takes us. And I guess finally, we could also talk about a W, a weight-based flow rate in newtons of fluid per second flowing past a given point. So, for example, if we have a cubic meter of water, well, if a cubic meter of water flows in a second, well, that cubic meter of water, I guess if it flows past a point in 1 second, the flow rate is 1 cubic meter per second. But the mass flow rate would be, well, what's the mass of a cubic meter of water? Isn't that 1,000 kilograms? So that equivalent quantity of water could be called 1,000 kilograms instead of a cubic meter of water. Not just different units, but a different quantity, in fact. And finally, a weight-based flow rate of, well, if it's 1,000 kilograms per second that's flowing, I guess that's 9810 newtons of water per second that's flowing in a weight-based approach. So consider the steady flow of fluid in a pipe. Let's not worry about flows going up and down and being unsteady. Let's just keep it straightforward here. So a steady flow means the quantity of fluid moving past any section is unchanging. It's not going up and going down in constant flow rate. And if we kind of consider two sections, maybe location or section 1 here, and maybe there's a pressure here, and there's a flow velocity, at least an average flow velocity here. And let me point out right now that when I talk about flow velocities for pretty much the rest of the course, we're really talking about an average flow velocity. There may well be some sort of a profile of velocities across the pipe. It might be that the velocity is fastest in the middle of the pipe and slower towards the edges of the pipe. Basically, we don't pay much attention to that at all in this part of the course. We kind of consider this velocity be the average velocity through this section. And then if we identify a second section further down the flow path, maybe the pipe diameter is different there. Maybe the pressure is different there. The velocity may well be different there. Even the elevations may be different here. This elevation, this distance, Z1, basically the height of section of the pipe 1 off of some reference level, the ground presumably, but really any reference level that's specified will do, because section 2 also has some elevation. So basically, by conservation of mass, kind of a pretty good, solid, reliable concept in physics, says you can't really add or change mass, right? As long as there's no nuclear reactions going on, no fission or fusion happening and mass is being changed, basically the mass of a closed system isn't really going to change. So if there's a kilogram of water per second flowing through here, and there's nothing being stored or added, there's no T connection here, there's no leaks or anything, well, the mass of fluid here and the mass of fluid here, they must be the same if there's a steady flow. So that's pretty important. So the mass flow rate at point 1 equals the mass flow rate at point 2, generally by the concept of the conservation of mass, which is pretty solid. But here's the thing. The mass-based flow rate is the same as the volume flow rate times the density of the fluid. Because volume times density gives you mass, and the fact that we're dividing by seconds to get flow rates doesn't make much difference. So we can kind of modify this. Oh, also, by the way, Q, flow rate, is equal to velocity times area. The volumetric flow rate, velocity times area. Again, an equation I think we're pretty familiar with from our fluid power course. So when we kind of combine these things, our sort of mass-based conservation law here, well, if the masses are rho Q and Q is VA, I guess we could rewrite this equation by saying that the density and the area and the velocity at point 1 is equal to the density and area and velocity at point 2. Now this is an odd statement to make here, this equation, because, well, the densities here sort of make things a little confused. What's density got to do with it? Well, density is kind of the relationship between the mass and volume flow rates. And this equation is called the continuity equation. We usually see it in a slightly simpler form. It's valid for all fluids, liquids and gases, compressible or not compressible. This works. But we don't normally bother with this full version of the equation because do you notice anything about it? The densities here, right? Density 1 and density 2. What could we say about those? Well, if we're going to deal with the flow of liquids in particular, liquids, we've seen this. We've kind of waffled on this issue. Are liquids compressible or not? Because in the hydraulics course, we sort of said that liquids are incompressible. And then this course basically started with an overview of some fluid material properties, and one of them was the bulk modulus, which is totally a measurement of the compressibility of liquids. Liquids are, in fact, compressible. When you squeeze them, they do get smaller. But not much, right? So it kind of depends on how you're looking at it. In lots and lots and lots of applications, the slightly incorrect statement that liquids are incompressible, it's close enough to being true that it's really, really, really useful. So we often apply it. And we basically save the compressibility of fluids for high pressure change situations where the small change in volume is going to be significant and needs to be dealt with and accounted for. But in lots and lots of cases, and lots of circumstances and ways of looking at things, it doesn't really matter. So if we say that the density is constant from section 1 to section 2, that density 1, density 2, they're the same thing, they're just the density of the fluid. That's a pretty fair approximation if the pressures are not too far different and nothing much has changed. And it's a liquid. And in fact, for gases, this tends to be true as well. Because you might think that, well, here's the thing about gases. Gases absolutely are compressible. So you'd think this would be only applicable to liquids where we could sort of cancel out this density from this equation. But in fact, you can do it with gases as well. As long as the flow rate of gas is not crazy fast, you can treat gas flows as incompressible as well. We tend to be in this course a little more concerned with the flow of liquids in pipes, just sort of for practicality reasons, I guess. But it's applicable to gases as well, as long as the gases aren't moving near the speed of sound. They behave essentially incompressibly. So this is sort of our new version of the continuity equation. A1V1 equals A2V2. So let's just try this here. So problem 1 in your activity for today. So we have this pipe here. The inside diameters at section 1 and section 2. So here and here, they change. 50 millimeter diameter inside the pipe here, 100 millimeter inside diameter over here, and we have water at 70 degrees Celsius flowing at an average speed in section 1 of 8 meters per second. Okay, so that's the setup. We don't know what's going on at section 2 just yet. We want to calculate a few things about this. We want to know the velocity at section 2, And we want to know the volume flow rate and the weight flow rate and the mass flow rate. And I'm not saying at section 1 or 2 for these because this kind of the point. These are all the same. The flow rates are going to be constant through this pipe. The flow rates don't go up or down. As long as there's no flow coming into the pipe or out of the pipe in between our two sections of interest, these three flow rates are going to be the same. So let's have a look at this. I'll project my iPad and we can try this out. All right. Okay, so I guess we need to find, the problem statement is find V2 and Q and big M and big W given a few things. Those few things are, well, stuff like D1 is given as 50 millimeters. D2 is 100 millimeters. And V1 is 8 meters per second. And that's pretty much all we know, except we need some material properties because we have water at 70 degrees Celsius. We're going to want the properties of that. If we look this up in Appendix A1 of MECH, I think, for properties of water at temperatures other than room temperature, I think what we find out is that gamma for the fluid is 9590 newtons per cubic meter. And that's water at 70 degrees Celsius. So our continuity equation is A1V1 equals A2V2. And we know V1, and we're after V2. It's one of the things that we're after. So let's rearrange this equation and say that V2 is A1 V1 over A2. Now, we could absolutely calculate the areas at 1 and 2, those two areas, because we know the diameters at both points. So we could actually do something like this. We could come over here and say A1 is pi by 4 D1 squared. And since we know D1, we could work this out and get our number here. But maybe we don't need to, because maybe we can just leave it in this general form and see what happens. Because we can kind of rewrite this equation. I guess we could put in the expression pi by 4 D1 squared over pi by 4 D2 squared times V1. And the charming thing about that, of course, is the pi by 4s cancel, and we don't actually need to calculate the areas, which is a good thing because they're areas of a circle. They're circular areas, so it means that when you calculate them and write them down, you are introducing rounding error because it's got a pi in there, right? So this area is going to be a decimal that goes on forever. Why don't we cancel those pi's out, save ourselves some rounding error, keep it a little bit simpler. So I guess what we have here is 50 squared millimeters squared over 100 squared millimeters squared times 8 meters per second. And I think out of this pops V2 then is 2 meters per second. Fair enough. The flow through here is fast, 8 meters per second, because the pipe is skinny. Up here, the pipe gets fat, and the speed goes down. Hey, look at that! Look at that big, long velocity vector here. A little shorter one here. Well, that's kind of what happens, eh? When pipes get big, the velocity gets small, and not in proportion to the diameters. Because look what happened to the diameters. Here, the diameter is 50. Here, it's 100. The diameter doubled. What did the velocity do? Did the velocity get chopped in half? No, it didn't go from 8 to 4. it went 8 to 2. It got chopped in half twice. That's because it's about area. The relationship is about the area relationship, not the diameter relationship. It's the diameter relationship squared. It's not 50 over 100. It's not a half. It's 50 squared over 100 squared. It simplifies to 1 over 4. So as the area gets big, the speed goes down, and it does that in a squared relationship that's here. So 2 meters per second is our velocity at point 2. We wanted to find out Q, M, and V. Well, the equation says that Q equals AV. Which A? Which V? Well, I guess you could say A1, V1. That would be okay. Or you could use A2, V2, whichever. Either one would be perfectly fine. I would tend, all things being equal here, do I want to evaluate this expression or this expression? And of course, they should give you the same thing because they're equal. But there's a slight reason, I think, to prefer that calculation because I was given velocity 1. I had to calculate velocity 2. There it is there. There's my result. If I use this in a calculation, I kind of have, I guess, the added risk of maybe somehow this is wrong, so my next calculation would be wrong. So there's a slightly strategic reason to choose this version of the calculation because it doesn't rely on our calculations. It's from given input values. Really makes almost no difference, of course, though. So I guess that's equal to pi by 4. D1 squared V1, which I guess is pi by 4. Diameter, oh, hang on, let me give myself a little bit more room for this calculation. So Q is pi over 4 times the diameter squared. The diameter at point 1 was 50 E negative 3 squared meters squared. That's me putting the D1 squared term into base units with scientific or engineering notation. And V1 we said was 8 meters per second. That's our flow rate. We look at the top. At the top we got cubic meters. On the bottom we have seconds. Well, that's good. That's the way it works out. But the thing is, of course, a cubic meter is a pretty big hunk of volume. A cubic meter, that's a lot of water. A lot of warm water, 70-degree water. So when we calculate flow rates for things like piping systems in cubic meters per second, we tend to get little tiny numbers. I think this one works out to be that Q is 0.01571 cubic meters per second, and there's nothing wrong with it being a little small number. It's just that it's quite a big unit of flow for things like flow in piping systems. Cubic meters per second is a pretty good unit for flow of water in like a river or something, because then you get sort of good numbers. But in piping systems, this tends to be a very low number, very small number, which is perfectly fine, except that I find for very small numbers, it makes it hard to do a sanity check. If there was an extra zero, if there's an extra zero there, if it wasn't 0.0157, if it was 0.00157, it doesn't really help me much with the sanity check. I kind of find it hard to imagine what 0.01571 cubic meters looks like. How big a hunk of volume is that? It's kind of too small for me to wrap my head around. If I converted this to liters per second, I know what a liter is. It's a big bottle of water volume kind of thing. But this is the base units. We very often use liters per minute or gallons per minute for these flows, but the base is cubic meters per second. We also wanted the weight-based flow rate, and the equation says it's gamma Q. Well, I have Q, and I have gamma. So I guess my answer is, what did we say gamma was? 9590? 9590 newtons per cubic meter. Times how many cubic meters per second? 0.01571 cubic meters per second. Cubic meters cancel. I'm left with newtons per second, and W seems to work out to be 150.6 newtons per second. Every second, 151 newtons of water flows through any given point in this pipe. And finally, the last one, the mass-based flow rate. Well, the equation for that we could use is its density times Q. Similar to this equation, this one uses weight density and its weight-based flow rate. This is mass-based flow rate, and it uses the mass density, of course. So very much the same thing, only I didn't look up. Oh, well, I guess I could have. When I looked this up, I could have also looked up and found out that gamma of this water is 978 kilograms per cubic meter. So 978 kilograms meter cubed times Q, 0.01571 cubic meters per second. And we end up with our mass-based flow rate being about 15.4 kilograms per second. And by the way, that kind of numerically works out to liters per second, because a kilogram of water is pretty close to a liter. It's about 15 liters per second, which I find kind of a friendlier kind of a flow rate. Kind of know what 15 liters looks like. That's a good size flow, 15 liters every second. So the other ones are perfectly valid for mathematical calculations. A little awkward to work with sometimes for sanity checks. All right, let's push on here. Oh, yep, here's our solutions in the lecture notes. Okay. So, we need to know what we're going to pump our fluids through, because there's a variety of, well, I guess generally they're called conduit, but conduit just means any sort of long, round, hollow thing through which you pump stuff. Often conduit is kind of applied to electrical installations, and conduit is the sort of metal or plastic pipe that you run wires through. But it's got a wider, broader meaning in mechanical engineering. Conduit is sort of what we're talking about when we're talking about pipes and tubes and hoses. They're all sort of conduits. So we have a variety of them to use for fluid transfer. There's steel pipe, standard steel pipe, but there's also steel tubing, and they're similar in that they're both long holes surrounded by steel, but they're spoken of, they're specified, they're talked about and used a little bit differently. Steel pipe generally is bigger and more robust than steel tube, but they're kind of similar, and they're used for slightly different purposes. But there's also other ones. There's copper tubing and plastic tubing for things like household plumbing applications and industrial plumbing, and there's ductile iron pipe for lower pressure water flows and things, and then there's hydraulic hoses, and there's all sorts of these that we're going to potentially encounter, but we're going to keep our focus to just a couple of them. Basically pipes and tubes for the most part. Standard pipes and tubes. So standard steel pipe, very, very common for flow for all sorts of things, often larger flows. And the way that they're designated is by their nominal pipe size, their NPS number, and a schedule number. So the way that you kind of talk about a pipe, the way that you describe a pipe, it's not by talking about its wall thickness and inside diameter or outside diameter. It's two numbers. It's the nominal pipe size and the schedule number. The nominal pipe size refers to the nominal outside diameter. And the thing is, it's very often not really all that close to the actual outside diameter. And it's not just a tolerance difference. It's not like, it's more like I kind of like to compare it to like a 2x4. You can go to Home Depot, buy yourself a 2x4. And if you take it home and measure it, it's not 2 inches by 4 inches. It's just called that. It's named a 2x4. It's nominally a 2x4. But in fact, it's 1.5 inches by 3.5 inches, and it's always that. Same thing with pipes. A 1-inch pipe should be a 1-inch OD. It's nominally a 1-inch OD. But when you go and look it up, it's not 1 inch plus or minus some small tolerance. No. It's nowhere near 1 inch. It's something else entirely. It's just called 1 inch. That's what the word nominal kind of means, eh? Nominal includes nom, which is French for name. It's kind of the name of the thing. And the schedule is basically just a slightly meaningless number that just refers to the table where the information on this pipe is tabulated. And there's a bunch of different ones. 40 and 80 are really common. Schedule 40 pipe and Schedule 80 pipe are pretty common. But there's a whole bunch of other schedule numbers. And basically, as the number goes up, the wall thickness of the pipe goes up as well. A high schedule number tends to be a thicker walled pipe, good for higher and higher pressures, with the same outside diameter. Some of them are common, some less common. but 40 and 80 are pretty common standard pipe sizes. And one charming thing is that all pipes of the same nominal size, they all have the same OD. Doesn't matter what their schedule is. So a 6-inch Schedule 40 pipe and a 6-inch Schedule 80 pipe, on the outside they look the same. Same size outside diameter. It means that you can use the same clamps and hangers and hardware and stuff for them because the OD is the same. It's the inside that gets different with the higher numbers. If you want to do this in metric, well, really all we do is replace the NPS, the nominal pipe size, with the metric version, which is called its DN. It's a French thing. It stands for diameter nominal. My French isn't very good. Diametre nominal, I suppose. In millimeters instead of inches. It's still wrong. It's still just a nominal thing. You can't really take it at its word. If you're talking about a 25 millimeter pipe, that's the same thing as a 1-inch pipe, in that neither of them are 1 inch or 25 millimeters. So they talk about the same thing. Let's see. We'll have a look at some data here to clean this up. Let's look at problem 2 and try this out. And this is just, I'd like you to actually do this, really. Use the appendix in the back of MECH and fill this out. Go and literally find this information for an 1.5-inch Schedule 40 pipe. And then the same thing for an 1.5-inch Schedule 80 pipe. It's on the next page in the textbook. And we need its outside diameter and its inside diameter and the wall thickness. And interestingly, usefully, the flow area. So you don't have to calculate it for yourself. When you go and look up information on a pipe, one of the main things you need is the flow area. What's the inside area? And instead of just getting the ID and going, all right, give me a minute to do a pi by 4 this thing squared business and you'll get the flow area. No, you don't have to. It's an important term. They just give it to you directly, as well as this term, and you could calculate it, and it better work out to be the same number if you do. So please pause this video, go sort this out, write these values down. Make sure that you're perfectly happy and comfortable looking these numbers up in the back of your textbook. All right, I bet you've done that, and I bet you have numbers that look kind of like this from MECH Appendix F. This is what I found. The outside diameter of an 1.5-inch pipe sounds like it should be 1.5 inches, and isn't. It's 1.9 inches. And it's that for a Schedule 40 and a Schedule 80 pipe. The difference isn't the outside diameter. Between these two pipes, the difference is the inside diameter. This one's smaller. This one has a thicker wall, and that's kind of the main idea, right? As the wall thickness goes up, the inside diameter goes down, so the flow area goes down as well. Charming thing about a Schedule 40 pipe compared to a Schedule 80, it's got more inside area. A Schedule 40 pipe is bigger inside than a Schedule 80 pipe of the same nominal size. That's because the wall thickness is taking up more space, and that's basically it. Notice table F1, it gives the diameter in inches and millimeters, but that same table gives you the flow area in both square feet and square meters. Just want to be a little bit cautious about the units as we use them in these looking stuff up in tables. So this is what we found. Schedule 40. Let's see, an 1.5-inch pipe nominal is also called a 40 millimeter pipe. They're the same thing. Hey, it's not like bolts, eh? Pipes aren't like bolts in that you got a metric thing and a whole other US thing, right? Inch series bolts and metric bolts are different beasts. They're not interchangeable. You can't put a metric nut on a US bolt. They just don't match. A few times they kind of come close. I think a 17 millimeter bolt and a 3/4 bolt are kind of close, but that's just sort of the way it happens. In pipes, it's not like that. The pipe is the same pipe, whether you talk about it in metric or you talk about it in US units. It's the same pipe. It's kind of a thing worth knowing, eh? You don't really want to complain if you buy some pipe. If you buy an 1.5-inch pipe and they send you a 40 millimeter pipe and you're all mad because it's metric and it won't fit, no, it's the same thing. It's the same pipe. It's just a different way to look at it. So we got Schedule 40 and Schedule 80 on these two tables in the back of MECH, and this is the data that we found. No big deal, but a few things worth noting about the units and how to look these things up and stuff. And also keep in mind that the data in the back of MECH, it's textbook sample data. It's not like the exhaustive big honkin' list of all the pipes there is. For that, you need bigger resources. The Machinery's Handbook might be good for that, but also other online sources for different pipe sizes. Let's try another one. We have now water flowing, US unit problem. 180 degree Fahrenheit water flowing at a rate of 72 GPM. Uh-oh, it's always messy with the US units, eh? Gallons per minute, we'll have to worry about those units probably. So it flows through a 3-inch Schedule 80 pipe, through a reducer here, to a 2-inch Schedule 40 pipe. Now, why does it do this? Well, never mind, eh? We're just wrapping our heads around the basics here. Hey, I hope you find the stuff we're doing today. I don't expect you to find it enormously fascinating, to be honest. This isn't one of the most interesting lectures in this course, I think. It is kind of foundational, because the stuff that we're doing in this lecture, not meant to be really, really hard and challenging, but it does tend to be sort of step one for a lot of the stuff we're going to do in the rest of the course. So we want to kind of just make sure in this lecture that we're good and comfortable using our resources and understanding what they mean and what they don't mean. So we want to find the weight flow rate and the velocity in both pipes. And you know what? Pretty soon we will be done talking about weight flow rates and mass flow rates as being things that exist and things we can calculate and consider, but generally we don't. Generally we use Q, the volumetric flow rate. All right. So let's work this problem out together as well. So, as usual in these problems, we're going to have to look stuff up. Q, we're given Q, and it's 72 GPM, but I would write it as 72 gallons per minute. If I'd like to know that in some kind of base units to be getting on with, it's maybe not a bad idea at the beginning of the problem to convert it. You can if you want, or if you're doing this in MathCAD, it does its own conversions, or you can use the Waterloo method continuously to do your calculations. I think I'm going to convert Q to base units right up front. So let's see. I know that there is... how do I do this conversion? Hang on. I'm going to do it this way. 1 cubic foot is 7.48 gallons. You can look up unit conversions in the back of MECH. And 1 minute is 60 seconds. So my minutes cancel and my gallons cancel. And I'm left with cubic feet per second. And I think my flow rate Q works out to be 0.1604 cubic feet per second. Let's see, for water at 180 Fahrenheit, I think gamma, if we look that up in table A2, gamma is 60.6 pounds per cubic feet. And we're after the weight-based flow rate, W. Well, the equation is it's gamma Q is W. I guess that's gamma is my 60.6 pounds per cubic foot times Q, which we said was 0.1604 cubic feet per second. The units behave, the cubic feet cancel, pounds per second remains. I guess W is 9.72 pounds of fluid per second. Also, I didn't really leave myself all that much space. I'm going to shrink this down a little bit, give myself some room because I can, and push on with this calculation. So at section 1, maybe I'll zoom in a bit here. At section 1, this is a 3-inch Schedule 80 pipe. You might write it that way as a short form. And what we find out is the area at section 1 works out to be 0.04590 square feet. And at section 2, we have a 2-inch Schedule 40 pipe. So its area at section 2 is smaller, 0.02333 square feet. And this looking stuff up about pipes is going to be a pretty common thing for us to have to keep doing in this course. So we wanted the velocity at section 1. Well, in general, Q is VA. So V is Q over A, and we could throw the subscripts on there. We could put a subscript on the Q, but you don't really have to talk about Q1 and Q2. It's just Q. It's the same flow rate through the pipe. That's pretty reliable. Let's see. That would be 0.1604 cubic feet per second divided by an area, A1, 0.04590 square feet. Kind of good thing that I did this calculation in, I did this conversion up here to cubic feet per second. Not inches, but cubic feet. Partly, notice that the inside of the pipe is given as square feet. It seems to be about feet, not inches. Mott's kind of a big fan of the feet instead of the inches, it seems, and that's fine. So they cancel. These square feet cancel those, and I'm left with feet per second, perfectly valid unit of velocity. So V1, 3.5, well, 3.49 feet per second. What about V2? V2 is smaller, right? Section 2 is a smaller area than V1. So what do we expect the velocity at 2 to be if it's a smaller area? Well, if the area goes down, the speed goes up. How does it actually play out? Let's see.
1 cubic foot is 7.48 gallons.
Ha! I just realized I've been talking with my microphone muted. I beg your pardon. I'm not going to redo this, though. I think you're probably following it for the last moment. Here's what we got. If we determine this area. If we get a pipe with an area of this, when we put 10 GPM through this area, we will get 1 foot per second of flow velocity. Well, that's well enough, but you won't get this size because why would that be on the list of pipe sizes? So we need to go and find a pipe whose area is this, or more or less. How's that threshold work? Is it pretty clearly more? We want a pipe whose area is this or bigger so that we get a speed of 1 feet per second or less. Okay, and the feet squared is a good thing. I want this number to be in square feet because I have to take this number to a list, and the list has its numbers in square feet. I don't want square inches, that's a different number. I don't want square millimeters, that's a different number. My tables are in square feet and square meters of all things. So let's have a look. If we do take that size to Appendix F, is it? The pipe tables in the back of the book. I think what we end up with is a 2.5 inch Schedule 80 pipe. And the way that we do it is here's Schedule 80. And here's the smallest pipe they have, presumably the cheapest pipe. Will it do? No, because its area is this. It's tiny, 0.000. I want 0.02. So this one's no good, and this one's no good. And I keep looking for the smallest pipe that'll work by finding one with the area. And this one's not quite any good, but close. This is the next size up. It's a 2.5 inch Schedule 80. So that's the one for us. That's pipes. Steel tubes are a little different. Steel tubes they're mostly used for hydraulic systems and heat exchangers, fuel systems, kind of smaller flow systems. And they're also specified differently. We talked a little bit about this in the fluid power course as well. Unlike pipes, the nominal outside diameter is actual. So a 1 inch tube, unlike a 1 inch pipe, a 1 inch tube really is 1 inch big on the outside, with, of course, a very small tolerance, but pretty small. A 1 inch tube is pretty bang on a 1 inch OD. So no schedule numbers for tubes either. Tubes are specified basically by the outside diameter and the wall thickness, and they're both sort of actual as well as nominal values. No schedules. And you can get different diameter tubes in a variety of wall thicknesses. Sometimes for small tubes, maybe just a couple of different wall thicknesses. But for bigger tubes, there tends to be kind of a wide range, maybe 3 or 4, or 5 or 6 different wall thicknesses you can have. And again, like pipes, as the wall thickness goes up, the inside of the tube gets smaller, but the outside stays the same. So all 1 inch tubes have the same 1 inch outside diameter, and it means that you can use clamps and things like that for 1 inch tubes. They all fit. The common sizes in inch series tubes they go in 1/8 increments for common sizes, but by actual standard sizes, it's 1/16. So anywhere from about 1/8 of an inch for quite a small tube up to about a 2 inch. Maybe they get sometimes bigger as a standard, but a 2 inch is getting to be a pretty big tube. And if you need tubes bigger than 2 inches, it's time to start thinking about pipes instead of tubes, it seems. And they're specified in Appendix G in our textbook. So let's try one with a tube. What's the flow velocity in meters per second? We're in metric this time, oddly. So we got a bit of a mix here. We have this tube, a 3/4 by 0.65. That means the outside is 3/4 of an inch in diameter, pretty much bang on, and the wall thickness is 65 thousandths of an inch. But the flow rate is in metric. It's 8 liters per minute. So it's like a metric application in which we're using this inch series tube. Anyway, we want to know what's the flow velocity that happens here. So let's solve this together. Not too difficult, because if we go to the tables, for a 3/4 by 0.065 wall thickness tube, what we find is in the appendix, the area, well, the area is given, again, in 2 units, I think. You get the area in square meters, but also in square feet for the same tube. Since this is a metric problem, I guess we want the area in metric. 1.948 times 10 to the negative 4 square meters. The other thing is, you don't actually need a table for tubes. You do for pipes, because pipes are lying to you about their size, but tubes aren't. Tubes are honest. Tubes tell you the truth. Tubes tell you how big they are, and they're not exaggerating. So if we know that basically this tube is shaped like this, this is 3/4 of an inch, and this is 0.065 inches. So we can totally calculate the inside diameter and then calculate the area, and we don't actually need to look anything up. You can't do that with a pipe, because the pipes, you wouldn't know what the diameters really are, because they're just nominal. Anyway, we don't have to. Also, if we did it this way, we would have an answer in US units, and we kind of wanted it in metric. And here we didn't even have to do a conversion. We just looked the number up. So, what's the flow velocity? Well, the flow velocity is Q over A, which is 8 liters per minute, divided by an area of 1.948 E negative 4 square meters. And I guess we got to sort out the units. Let me give myself some room here. Well, what's the deal with liters? There's 1,000 liters is 1 cubic meter. That gets rid of the liters. And let's get rid of the minutes as well, because 1 minute is 60 seconds. So the minutes cancel. I'm left, oh, wait a minute. And now the square meters cancel the cubes. And I'm left with meters per second. And I guess it means that my velocity here is about 0.685 meters per second. About 0.7 meters per second is the fluid velocity that I'm going to get. There we go, there's our solution. With a few alternatives, we could have calculated the area ourselves and then done a unit conversion. We get pretty much the same number. And here's our data in Appendix G. Hey, by the way, Appendix G is not very complete. It generally, there's usually more wall thicknesses than are provided. Appendix G doesn't show all the options for wall thicknesses. Again, these appendices in the back of MECH, they're sort of sample data. They're not really the book you want to have for actually looking these things up to see what's available. It's sort of sample size stuff. So if we want to choose pipes, and we want to choose our pipes by making them big enough to carry the flow, at a reasonable speed. And that's pretty much the trick. Basically, we generally know the flow from the application because we're designing a log splitter and we're going to use a pump that puts out 10 gallons per minute or whatever. Usually the flow is a number that we can get at, and it's kind of required to size your pipes. Also, the pressure. The pressure is required to help you choose a pipe with a big enough wall thickness, but it's kind of second. First of all, you need a pipe big enough to carry the flow rate at a decent velocity. A decent velocity meaning slow enough, and we'll see how to work that in a moment. But once you find the inside flow area of the pipe, well, that's fine. Now what you need to consider is the pressure that's going to be inside the pipe, and make sure that you choose a pipe whose inside flow area is enough to carry the flow and whose wall thickness is enough to support the pressure without bursting. We're going to kind of mostly pay attention to the first part, the size based on flow rates. And it's fairly intuitive, I think. There's nothing very counterintuitive about it. The idea is that for a given flow rate, the fluid velocity goes up when the pipe size goes down. Smaller pipes, higher speed, of course. High velocities, though, are a problem, as we kind of know. At high velocities, we basically waste more energy. There's also higher pressure drops. That's a consequence of wasting that energy. There can also be noise, squealing pipes, turbulence, heating of the fluid, because that's where the energy goes into heat. So we don't want the speed to be too high. What's an appropriate fluid velocity? Well, I mean, an appropriate fluid velocity, it kind of varies with the application to an extent. For example, in hydraulic systems, we sometimes say 20 feet per second for pressure lines. That's the maximum. And some other speed for return lines. For this course, we can kind of fine tune it. This table is in MECH. So it says in a hydraulic system for suction lines. The suction line is the little small part of pipe that goes into the pump. There's just one. It's just little. It's a short usually, but it's usually the biggest line in the system because you kind of want the fluid flow, the flow rate or the flow velocity in the suction lines going into your pump quite slow. Not much resistance to flow at all. 2 to 4 feet per second. Make the suction line that feeds the pump, keep the speed of the flow in that line under 4 feet per second. They kind of give you a lower range, and that's really to just sort of limit how big a pipe you should use. This says 2 to 4 feet per second. If you use a pipe that's too small, the speed would be higher than the 4, and that's no good. If you choose a pipe that's too big, though, all that means is the speed would be less than the 2. It's not really a problem. It's just that you're getting a pipe that's so big that it doesn't need to be that big. That's the thinking. Same thing with meters per second version here. For discharge lines, it's an odd thing to call it, but pressure lines, they're saying 7 to 25 feet per second. I've always used 20 feet per second myself as my guideline for pressure lines. Keep the speed under 20. Here they're saying 25. And the fact that nobody quite agrees on these, well, it's because it's not a hard and fast thing. It's a little bit like saying, what should the speed be on the QEW going from St. Catharines to Hamilton? It used to be 100. For years, I think the speed was 100. I think now it's 110. It's not like anything changed other than just people's opinion about it. I guess we decided we'd tolerate a few more dangerous accents and get everybody home a little quicker. Some sort of a trade-off here. So it's not like anything bad happens at 26 feet per second. It's just that that's getting a little fast. If the maximum speed in your pipes, your pressure lines, in a hydraulic system is less than 7 feet per second, it kind of suggests, wow, you really bought some big tubes for your hydraulic system. You didn't need to get them that big. You could have saved yourself some trouble and some money by using smaller ones and keeping it, closer to the 20, not way down by the 7. Anyway, those are some recommended velocities in fluid power systems. We're going to talk about this a little bit more because there's other ways of doing this. So it's not like the answer to the question, how big a pipe do you need, has a fixed answer. The answer kind of depends on what are you using as the velocity limit, because it tends to be slightly arbitrary, slightly open to some give and take. There's another one here in MECH. This is in MECH. There's a figure in Chapter 6. And look, it's for a Schedule 40 pipe, either in NPS, US units, or in millimeters, diameter nominal or nominal pipe size or diameter nominal. So basically pipe size in millimeters or inches nominal. And we have these two lines. One for, again, for suction lines, which is a little odd. That's the slightly vacuum pressure line leading into a pump. For all other lines, they're calling discharge lines, and they're saying follow this line for these flow rates. So if you have a 15 GPM system, that's cubic meters. This is the volume flow rate in gallons per minute. And look, it's a log scale here, logarithmic scale. This one's a little odd as well, kind of logarithmic this way too. Anyway, that's all right. So it tells us that if we had 100 gallons per minute flowing in a pipe, then the discharge line, 100 GPM, you want at least an 1.5 inch pipe for that kind of flow. Or a little higher. Actually, that's a little small, isn't it? It's more like 90 GPM would be good for an 1.5 inch. So we can just use this to get basically kind of a rough idea of some pipe size recommendations. This is only for a Schedule 40 pipe. We could find similar graphs for Schedule 80 and other sizes. Or we could basically figure out what velocities are involved here and use the velocity limit, which is what I kind of prefer. I kind of prefer a specification saying, don't go past this velocity, get a pipe big enough given that limit. Let's look at that in problem 6, where we want to, basically, we're speccing out part of a hydraulic system here, and we want to find a steel tube to be used in the return line of a log splitter. Now, the hydraulic system has a pump flow of, let's say, 20 GPM. So 20 GPM comes out of the pump, and the cylinder has a 4-inch bore and a 2.5-inch rod, and we want to size the return line. Now here's the thing, and I hope we remember this from the fluid power course. If we have a hydraulic cylinder, single-ended, as we do, 4-inch bore, 2.5-inch rod, and we put 20 GPM into the retract port, the piston retracts, and we push out the oil on the other side. And you may well, I hope you do, I hope you recall that the flow coming out of the extend port, the return flow, it is not 20 GPM. 20 GPM going in, more than 20 GPM coming out. We call that flow intensification, and it's a consequence of the area ratio. It's a consequence of the fact that the retract area is little because it's missing a hole out of the center where the piston rod goes, and the extend area is always bigger. And if the extend area is a lot bigger than the retract area, then this intensification effect is dramatic. It's big. It's significant. For instance, if you had a very big piston rod, if you had a 4-inch bore, and if the piston rod was like 3.5 inches, well, that retract area would be just a little thin red sliver of a ring. 20 GPM to go in, and lots more would come out. This area ratio, it is what it is. We'll calculate it. So we want to choose a return line, not based on the pump flow. The return line carries the intensified flow while the cylinder is retracting, and a de-intensified flow while the cylinder is extending. The de-intensified flow is not our problem because it's a lower flow. We want to make sure our line's big enough for the highest flow that it sees, which happens when the cylinder is retracting. Let's see how we do this then. So we need to know the flow, and to get the flow, it's going to have to do with the, we want to know what Q return is. It's basically about the area ratio. So we need to calculate the areas, because the return flow, I'm going to just call it Q, it's going to equal Q pump times the area ratio, which is the extend area over the retract area, which I guess is 20 GPM times, well, I guess it's pi by 4 times 4 inches, 4 squared inches, over pi by 4 4 squared minus 2.5 squared inches squared. When we work that out, I think we get an intensified flow. It's significant. It's 32.8. 33 GPM, basically. That's the intensified flow. During retraction, 20 is going in, and 32.8 GPM is coming out. If you've forgotten how that works, really refresh yourself from your hydraulic notes from last semester and make sure that this is completely comfortable to you, because we've talked about this a fair bit in the past. That's our flow. We need a return line big enough to carry that flow at something like a decent speed. Well, what are we calling a decent speed again? Well, if we go back to this slide 24, or the figure in MECH, doesn't it say that for return lines, the velocity should be 4 to 13 GPM? And at this point, you might go, well, I mean, which is it? 4, 13, anything in between? I need a number, Neil. I can't work with a range of numbers, so you sort of pick one, don't you? What if we go with the smallest one, right? Like, we want to basically decide what's the smallest tube we can get away with, or what's the biggest tube that would be before it gets to be overkill. Let's see. So the area that we need is Q over V, and Q is 32.8 gallons per minute. And if we're going to go with a velocity of, sorry, that's not GPM, that was feet per second. 4 feet per second. If that's the speed we're going to use, that's the lowest speed. Let's find out what the area is. We got to do a few calculations here on GPM. Let's see, 1 minute is 60 seconds. And 7.48 gallons is 1 cubic foot. I keep forgetting that 7.48 conversion. Gallons are gone. Minutes are gone. Seconds are gone. And this feet kills one of those. I'm left with just square feet. And 1.83 times 10 to the negative. That's really messy. Pretty sure that's the size of a pipe I need. That's a big one though, eh? That's the one that'll give me 4 feet per second. That's as big a pipe as I need. Or a tube. We're going to choose a tube. Any tube bigger than that is going to give me a speed even lower than 4 feet per second, which is already my minimum. So this is going to give me the big one. And I guess if I go to Appendix G looking for a tube whose area is bigger than this, I think what I find is what I need is a 2-inch 065 tube. That's the one that'll do. Now, let's pay a little bit of attention to this, because there's a bit of a trick to this. Let's see. So here's our tube data for this problem, for our log splitter return line tube here. So we found we wanted to get a big tube. Let's get the Cadillac tube. Let's not get the smallest tube that'll give us a high speed. Let's give us a nice big tube that gives us that 4 feet per second. That's the one that's 183 times 10 to the negative 2 square feet. So that's the number I'm looking for in here. Let's see. These ones are all too small. I need 1.8 times 10 to the negative 2. Not quite big enough. This one, though, is, eh? This one, 1.9 times 10 to the negative 2. It will do the job. But wait, there's more. Because look, wait a minute. What about this tube here? This tube is even closer to 1.83. I wanted 1.83. This one's 1.835. It's just a tiny bit bigger than the tube I need, right? So shouldn't I choose this one? Because this one's a bit more overkill, eh? This one's even bigger than this one, but this one's big enough. Don't I want this one? Well, here's the thing. This is a slightly odd problem because what we're talking about here is a 2-inch tube with the thin wall or the thick wall. The thick wall has a smaller flow area, closer to what I want. This one, though, it's the same size tube. It's 2 inches, but this wall thickness is less, so I get more flow area. Well, that's just good. So why would I choose this one over this one? This one gets my flow area closer to my target, but at the expense of like an extra thick wall. You're not really getting what you normally get in these kind of trade-offs. There's not really any good reason to choose this one. Choose this one. Slower speed and slightly cheaper and easier to work with. Thinner walled tubes are cheaper and easier to bend and a little bit easier to work with than thicker walled tubes. Just that, but thicker walled tubes are good for higher pressures. It's a return line, so there's no advantage to it being good for higher pressures. Pressure in the return line is going to be pretty much, well, if not zero, then like 100 psi, not very high. All right, I think one more of these, and that is this is a cooling system, a big one. Delivers 400 gallons per minute of water to a cooling system in a power plant, shall we say. So we're going to use that graph, that log scale graph for pipe flows in figure 6.3 of MECH to make a reasonable initial selection for a schedule 40 pipe for the suction and discharge lines of the system. Here's the pump driven by a motor. It's going to suck water in through the suction line and discharge it, well, through the discharge line. And we want to find what is the correct choice of pipes that are just big enough, schedule 40 pipes, big enough but not too big for these applications. Let's just have a look at the solution for this one. So from figure 6.2, that's for 400 GPM, that's this figure back here. So we're at 400 GPM. I guess that takes us up for the suction line right there. So we're not quite at a 4-inch pipe, but we're above a 3.5-inch pipe. I guess it's a 4-inch pipe that we need for this, eh? At 400 GPM. And the discharge line, I guess the next size up is 3. I think we want a 3-inch and a 4-inch. A 4-inch suction line and a 3-inch discharge line. That's what it looks like. 3-inch and 4-inch. That'll do. That'll give us some speeds. If we wanted, we could go up another size and get even lower speeds. So what we're choosing, just using that graph kind of, instead of specifying velocities, it just tells us directly a pipe this big or bigger, and it doesn't really get into the velocities. It sort of leaves that in the background, but we can still calculate them. If, for instance, we choose the 3-inch schedule 40 pipe for the discharge line, that's what its area is going to be. And therefore, its flow velocity is going to be 17 feet per second. Same thing for the suction line. 4-inch suction line give you a slower, about 10 feet per second in the suction line. We could go up, each of those could go up one size higher if we wanted to. That'd be a reasonable enough thing to do as well. Slightly slower speeds, still kind of reasonable speeds though. If the speeds are too low, there's no problem with low speeds at all, except if the maximum speed in a system is always quite low, it makes you wonder why you bought such a big pipe to begin with. You kind of didn't need it, but there it is. You know, it's a little bit like taking your kids to soccer practice in some kind of great big off-wheel, super powerful vehicle. I mean, it gets the job done, but it kind of overkill if that's what you only ever use it for. But nothing really wrong with it, except it's kind of a waste of money using extra big conduits. Well, that's about it for this week, or at least for this lecture. This is sort of introduction to this whole topic that we're going to get into. We're going to be looking pretty extensively at something called Bernoulli's equation and its consequences, and in the ins and outs of that. And then we're going to expand Bernoulli's equation into something more powerful called the general energy equation. And it's all about flows and pipes, and it goes a good long way. But to get started for today, we just wanted to get a grip on the basics of conduits and using the resources at the back of MECH and what they mean and what they don't mean, and just get comfortable looking these things up and doing these calculations. So your homework, as always, is to thoroughly review these lecture notes. but also to have a look at MECH, read MECH chapter 6 and read section 6.1 to 6.5. And there's an example problem in that, problem 6.6. Work through that. And then there's these practice problems here. It looks like there's a lot of them. There is a lot of them, but they're also just little. Do all of them or as many of them as you feel you need to make sure that you have this idea very, very firmly in mind. Not enormously challenging new concepts, I don't think, in this lecture, but don't let that fool you. There's more complicated things coming. It's just we want to make sure that this stuff at least is rock solid as a foundation for the problems to come. Solutions are in the lecture notes here. And I think that's pretty much all I've got for you today. We have our test, I believe, in the CoLab class this week. See you then.